thank you for the nice introduction. And also thank you for organizing this mini symposium and taking care of everything. In the next 25 minutes, I would like to talk about new linear scaling methods and their acceleration with FPGAs and since the last year, more importantly, with GPUs. So you see that basically a little bit diverging from the title that is in the program, and also the content is a little bit diverging from what was given in the abstract, because the abstract was the one from last year, and we have implemented major new steps, which will be the focus of this talk today. So at first, I would like to start outlining the necessity for mixed precision, so mixed precision arithmetic operations for molecular dynamic simulations. And start with why, in the grand scheme of things, we actually want to do molecular dynamic simulations, in case there are some people here who might not be physicists or chemists. Namely, the general idea, just on a really rough scale, is to study the physical, chemical, and biological properties of large systems like solids, surfaces, and also most recently viruses, like here in this picture, the HIV-1 virus capsid soluted in water. And this overall system has about 62 million atoms, and that becomes very challenging for molecular dynamic simulations, especially if you base them on electronic structure calculations. So why do we actually need mixed precision for these molecular dynamics calculations? Here on the slide, you can see in the above table the estimated energy cost for operations, here in this case in a 45 nanometer process for half precision, so FP16. The addition is here given as roughly 0.4 picojoules, whereas as in single precision, so FP32, it's already estimated to be more than double that. If you go to multiplication here in the last column, you see that the difference is already a factor of 4. And for double precision, the difference is even larger. That means in order to do energy efficient calculations on our large HPC systems, for large systems like viruses and so on, we really need to be able to use mixed precision calculations to be energy efficient. Secondly, if you look at recent hardware advances, for example, here the NVIDIA A100 GPU, I've listed here the peak performance in teraflops for different matrix operations on the tensor cores. So here FP16 multiplies with underlying FP32 accumulate, gives you gigantic 312 teraflops peak performance. So realistically, you would get like 280 for sufficiently large matrices, but that's really a lot for such a GPU. If you go to higher precisions like the TensorFloat 32, which is similar to single precision, or to double precision, so here FP64, this gets sequentially lower, so that at double precision, you end up with a peak of about 20 teraflops. And you can see that in order to do these large molecular dynamics calculations, we actually should care about mixed precision and come up with a way to do calculations with these operations. From the chemical physical point of view, we obviously have to think about, is mixed precision good enough for our calculations? So, and in that sense, we have to think about what is the actual insight that we want to gain. And here you have to know that even though we're doing molecular dynamics, it's actually not the individual trajectory of every atom in this large virus or solid or surface that's of interest, because that would be a huge amount of data. If you have 60 million atoms and in every time step or in every few time steps actually store the position, that's a gigantic amount of data. And obviously it depends on the initial position and velocities of the atoms, which makes interpretation pretty cumbersome. Instead, we're actually interested in the so-called thermodynamical averages, which are given here. So in essence, they're just integrals over the phase space in position and momentum space. And they can be performed by doing suitable molecular dynamics calculations. Here one can also show that the noise from the numerical approximations from mixed precision operation can actually be compensated with a modified Langevin type equation that's given down here. So additionally to the Norman Newton's type equation, where we have here mass times acceleration equals forces. In our case, these are now the noisy forces that stem from the approximate calculation with lower precision. We also have a dampening term that's velocity dependent and has here a dampening parameter gamma n. Actually, with this dampening parameter, it can be shown that with the fluctuation dissipation theorem, you can use this dampening parameter to configure temperature. And if you then do a molecular dynamics calculation with that, you automatically sample the thermodynamical averages. It can also be shown that doing it this way, you can actually compensate for the numerical noise, and you can achieve accurate thermodynamical averages from lower precision arithmetic operations. In the previous equation of motion, you've seen that we actually need the forces of the atoms. The forces of the atoms can be easily obtained from the total energy of the system E by just taking the negative derivative with respect to the atomic positions. That means we actually have to model the total energy of the system now. And here it's important to include quantum mechanical effects and also long-range interactions. One way to model this energy is to actually model it as with an electronic structural theory method. That means to explicitly include the quantum mechanical nature of the electrons. That means, that implies that we actually have to solve a quantum mechanical electronic structural problem in every step. In a conventional approach, that would mean the solution of a generalized eigenvalue problem, where we here on the one side have the Hamiltonian H0, Ci would be the wave function coefficients, S is the overlap matrix, and epsilon I are the eigenenergies. Solving that in a naive way would give you a cubically scaling problem, which obviously will kill you once you go beyond 1,000 or 10,000 atoms. However, if we take a localized, sufficiently localized basis set for the representation of our electronic wave functions, we actually see that the Hamiltonian H0 and the overlap matrix become very sparse matrices. And that's essential for building a linear scaling method. One possible way for a linear scaling method actually is a so-called density matrix-based approach that employs matrix sign functions. So here the electronic energy, so the actually complicated part of the energy, is written just as a trace of the Hamiltonian with the so-called density matrix. And then the density matrix can, at zero temperature, can be written as terms including here the sign function, the overlap matrix, or clear the inverse of the overlap matrix, the Hamiltonian, and the chemical potential. The one fact you should focus on here is the so-called matrix sign function. So this term here in the back is actually a matrix, and this is the sign function of a matrix. You might be wondering, what is the sign function of the matrix? The sign function of the matrix is simply the analogon of the sign function for a scalar, which is written here. So just x divided by the absolute value of x. If you write that a little bit, you can put in the matrix in the same term and know basically how you would perform that for a matrix. However, you see here that we have to calculate the inverse square root of a matrix, which is a very cumbersome operation. That's why in practice, actually this is performed as an iterative method. Here's this, the simplest order, so-called Newton-Schultz iteration, where you start with the zeroth iteration with the matrix, which should have to obey additional certain normalization constraints for this scheme to be convergent. And then in every step, you just compute xi plus 1 as this equation here, which, as you can see, only includes some scalings and some matrix multiplications. And one can show that this actually converges to the sign function of A. Important here is that we actually only have to perform multiplications, and multiplications are pretty simple. This all in all gives us a linear scaling approach with the number of atoms, and we, as mentioned, only need multiplications of distributed sparse matrices. However, multiplications of distributed sparse matrices are usually bound by internode communication, because you have to distribute all the blocks, and then in the multiplications you have to do certain operations that look like all-to-all operations. This is where our new method comes in, the method that we call submatrix method. In the next few slides, I would like to outline the general idea of the submatrix method and then come to some results. So the underlying idea is that we want to estimate a matrix function, like a sine function or matrix inversion, for a large sparse matrix. So we have a sparse matrix here A, or the grayish fields mean fields with non-zero entries and white ones with zero entries. And we want to approximate some matrix sine function of that. The first step of the submatrix method is then to proceed column-wise. So we first look in the first column and identify all non-zero values. So that would be the first, second, third, and fifth row here. Similarly, for the second column, that would be the first, second, and the last column. In the next step, we create for every column the so-called submatrices here that we call TI, so submatrix 1 of the matrix A. For the first column, this is created by removing all rows and their corresponding columns where we have zero entries here. That means we remove the fourth column and the sixth column. We're ending up with a 4x4 submatrix, which is obviously smaller than the original matrix and denser than the original matrix. For second submatrix, for the second column, that would be a 3x3 matrix. Then we actually apply the matrix function, like the sine function or the inversion, to these submatrices individually. And in the last step, take the resulting column, like here this light blue column, and put it into the resulting column of the resulting sparse matrix. Here I've listed a few features that you should be aware of. Namely, instead of working on large distributed sparse matrices, the submatrix method decomposes that into many small dense matrices. These dense matrices are obviously suitable for dense linear algebra. The method is massively parallel because instead of working on one matrix, we have a lot of individual submatrices to which we have to apply the matrix function. And it is by construction a linear scaling approach. We've also shown that the results from it are sufficiently accurate to be suitable for molecular dynamics calculations. From this general idea of the submatrix, you can derive several variants of submatrices, depending on to which matrix you apply it and where you generate and how you generate the matrix elements of the submatrices. First of all, you can either act on the non-orthogonalized matrices, so H0 or S, or on the orthogonalized matrices. That would then give you either orthogonal or non-orthogonal submatrix method. You can also, the second aspect is then what you do with the matrix elements. You can either transfer them from the other nodes. That would make you give you a global submatrix method, and you can also generate them again locally, which we then term as a local submatrix method. So our first approach, which we actually wanted to present last year at PASC, is what we call the orthogonal global submatrix method. This works by directly acting on the sine function here. So we basically first compute this term here in the bracket, which is a matrix, and then only apply the submatrix method here to the sine function. That's orthogonal in the sense that here in the back, that's basically orthogonalized matrix. And this is already seamlessly integrated into CP2K and is compatible with all electronic structure approaches that are compatible with the linear scaling environment in CP2K. However, this requires a few global sparse matrix multiplications here for these operations in the back. And we've shown that this already scales better than a similar Newton-Schultz iteration approach, which was till now the preferred approach. You can see that here quickly in plots. So on the x-axis, we have the number of CPU cores. On the y-axis, the time. This is a weak scaling calculation. So the amount of work per node is always, per CPU core is always the same. And here in the dashed line, you see the parallel efficiency for the Newton-Schultz method, and in the blue dashed line for the orthogonal global submatrix method. And you see that at some point they start to scale similarly due to the global matrix multiplications that are still required in this variant of the submatrix method. So here's actually then where GPUs and FPGAs come in, namely this action of the matrix function onto the individual submatrices can be easily offloaded to accelerators. and on accelerators, you only need generalized matrix multiplications if you calculate the matrix function iteratively as shown before. Here down below, just some initial performance results here from consumer grade NVIDIA GPUs, comparing the peak performance on the tensor cores to the achieved sign iteration, including transfers. Similarly here for the Stratix 10 FPGA, comparing the peak or matrix multiply peak to sign iterations. And here you see this discrepancy between the actual matrix multiplies and the sign iteration, including transfers, and that shows you that the performance is actually limited by the transfer from of the matrices from the host to the accelerator, then computing the matrix sign function there, and then transferring back. And the transfers are a problem. So we came up with a new method that we now call the non-orthogonal local submatrix method. That's our recent development within the last year. It's constructed so that you don't need any global matrix multiplications anymore. So you don't have an internode communication bottleneck anymore. And the entries of the submatrices are not transferred from other nodes or generated on the CPUs, but they're directly constructed on the accelerator, which eliminates the host accelerator communication as a bottleneck and makes the method more efficient and more scalable. However, this now has to be implemented individually for every electronic structure method. In this case here, we use the XTB approach, and we're planning in the next months to extend it to DFT. Now to the how it works underneath. So here, instead of just viewing the sign function as a matrix function to be approximated, we view the whole density matrix that depends on the Hamiltonian H0 and overlap matrix as the matrix function to be approximated. That makes it basically a non-orthogonal, that's why we call it a non-orthogonal submatrix method, because it acts on the non-orthogonalized matrices H0 and S directly. It's also, we call it local, because the submatrix construction is performed locally on the GPUs, and we don't have to transfer any matrix elements between host and GPU. Here's a short sketch of the implementation. So starting from the left here, we have on the host the overlap matrix and the Hamiltonian. From those, we generate their sparsity pattern, basically performing the steps of the submatrix construction in the sense of knowing which columns to take. Then we only transfer this column information to the GPUs. In the GPUs, we construct the matrix elements of the submatrices and then go further in the individual steps. So in the first step, in the transfer, instead of transferring n by n matrices from the host to the GPU, it's now just a linear scaling amount of data, if n is the submatrix dimension. In the second step, for the construction, we have to construct overlap matrix and the Hamiltonian matrix, which is a quadratically scaling step. Oh, sorry. Sorry for that. Then the actual computational intensive operation on the GPU is the computation of the density matrix and the energy weighted density matrix, which we additionally need for the forces later. This is again done here with iterative scheme, so that we can take advantage of the tensor cores in NVIDIA GPUs. Here you can see a short overview over the matrix multiply performance on the NVIDIA A100 GPUs in FP16 performance with FP32 accumulates over the matrix sizes here, and here on the y-axis the performance. The dashed line is the peak performance of 312 teraflops that's given from NVIDIA, and we can see that starting from matrix sizes of about 1,000 or so, we get about 60 to 85% of peak performance. This is possible by combining the normal cuBLAS kernels with additional CUDA streams and CUDA graphs to avoid certain problems, for example, with the launch latency for these small matrix multiplication kernels. In total, we get a scheme that has linear scaling amount of transfers from the host to the GPUs, so linear in the submatrix dimension, and the actual work, computational work, is cubically scaling. That makes the overall scheme very favorable because the ratio from transfer to computation is very nice here. We've implemented that in CP2K using dbcsr for the underlying sparse matrix storage, CUDA C++ for the matrix element creation kernels, and cuBLAS for the matrix operations. Right now, it's not yet in mainline CP2K, but this will happen in the next month or so. Now, finally, to scaling efficiency and performance of the method. All our results that I'm going to show you now have been obtained on the Qubits booster at Jülich Supercomputing Center, which has about 1,000 GPU nodes. And the important fact here is that there are 4 NVIDIA A100 GPUs per GPU node. So first start off with a weak scaling result for by quarter, so 1 million atoms per node, and then scaling up to 64 nodes corresponding to 64 million atoms. Here on this graph, on the x-axis, you see the number of nodes. On the y-axis, the time for the core routines of the non-orthogonal local submatrix method. And here you see the war time, which is essentially a horizontal line, which shows you that we have near perfect weak scaling with this method. Here we have basically a strong scaling result now for 102 million atoms, scaling from 128 nodes to 384 nodes. And on the one hand, you see the war time here, but more importantly, you see here the efficiency, which is very close to 1 and very flat, which also shows you that this method can achieve near perfect strong scaling to thousands of GPUs. Now here to a little bit more interesting example than by quarter, namely the previously mentioned HIV-1 virus capsid in water solution with about 62 million atoms in total. And here you can again see the number of nodes, up to about 400 nodes, corresponding to 1,500 GPUs. The time for the submatrix method, and then again here the efficiency is very close to 1, also for this inhomogeneous system, which shows you again that a very nice strong scaling result. Also, you might be asking, how close do we get to the actual peak performance that's available? That's shown here on for the same system as in the previous slide. Now, again, for 64 to 384 nodes. And on the y-axis, we have the achieved performance in the submatrix method. In the dashed line here, you see the peak performance, assuming 312 teraflops per GPU. And here on the red line, you see the performance of the submatrix method, which gives us here about 70% of the peak performance that's available in the tensor cores in FP16 multiplications with FP32 accumulate. You can also see here from this previously mentioned performance graph for matrix multiplications, where this about 68% come from. Namely, in this example, we have submatrix dimensions of about 1,200 on average, which is indicated here by the red line, which shows you that we get about 200 teraflops per GPU, which is about 2/3 of the peak performance here of 300 teraflops. And that's also already where I would like to come to an end and summarize what I've shown you so far. So with this effort, we've been able to extend electronic structure-based molecular dynamics simulations to more than 100 million atoms, most notably here for bulk water with 102 million atoms, and for 62 million atoms for the HIV-1 virus capsid. In total, the new non-orthogonal local submatrix method is an approximation method for large sparse matrices. It's massively parallel and communication avoiding, and can be nicely accelerated with GPUs and other accelerators to achieve a high percentage of the peak performance that's available. We've also shown that one can set up a compensation scheme based on a modified Langevin equation to compensate for numerical noise and achieve accurate thermodynamical averages that we are interested in from the physical side. In the end, I would like to acknowledge especially computing time from the Qubits Supercomputing Center on the Qubits booster, from Paderborn Center for Parallel Computing on the Noctua cluster, and funding and help from the European Research Council, Paderborn University, and colleagues at JSC and NVIDIA for important discussions about our GPU code. And I would like to thank you for your attention.